Hello, everyone. My name is Michał from Deep.BI, and I'm a machine learning engineer and a software architect there. If you have any questions during the presentation, you can also type them in the chat window. Maybe I will try to answer them during the presentation also, if there will be slide specific. Okay, so let's start. So what does DPI do? In short, we provide scalable end-to-end AI solutions. So we collect and process billions of events daily, track user behavioral patterns, measure content performance, and use AI-driven predictions in order to optimize target KPIs. Problems we solve range from marketing campaign optimization, on-site user experience personalization, churn prevention, or detecting frauds based on data anomalies. Our customers come from various industries such as media, marketing, retail, restaurants, insurance, pharma, and health. So completely different domains and data structures on which machine learning can be applied. I've also said AI at scale. So we do process data that will not fit on a single machine. We process over 40 billion rows every month, up to 100,000 events per second at peak hours. And we score around 100 million users each month, which is roughly 1 billion generated predictions. What is important for us? We do it everything is processed in near real time, usually with less than 1 second latency. And in the process of building our platform, we learned that creating a machine learning model is just a minority of work needed to be done. And in this talk, I would like to focus on this other 90% part, specifically how to effectively transform raw data streams into samples on which machine learning algorithm can learn and make predictions, and how to make it operational for data streams that in edge cases have virtually nothing in common. So to achieve our goals, we built an architecture that can handle it. So at core, there's Apache Flink, and it allowed us to integrate with both streaming and batch sources. We enriched the stream with additional features using stateful operations and async functions, and using additional control streams and broadcasted state enabled us to dynamically define any event filter or data transformation in multiple languages, such as Python or JavaScript, for example, and serve machine learning models, which is also important. And finally, when the data is enriched on Flink, it's indexed by both Apache Druid for real-time analytics and Cassandra for the score delivery. But the main point here is that we share the same, feature engineering code base between completely different machine learning projects. And make use of it in both real-time production pipelines and simplified batch experiments run by data scientists. At the core of our platform, we have Thinkjobs, including an abstract feature engineering framework that provides reusable templates for data transformations. Each feature defines how to extract values from raw events. Then it defines how to reduce this information with the previously accumulated state. And finally, it informs how to use this information to generate the final feature value. After this is computed, the result is merged with the raw event, and we have an image event at the output. Feature definitions can be updated at runtime and can depend on each other to minimize the state, which is also important at our scale. Now I'd like to share with you some of the design choices that we've made to make this happen. So first of all, we use the low-level DataStream API to implement custom process functions. In this simplified example, we have a process function that exploits. Maybe I can show. That exploits a feature processor that contains all the feature definitions. Here is provided while deploying the job. However, it could be also updated at runtime using a broadcasted state. Each operator has its state shared between the features, and we will use value state for that. And we use custom event timers to implement simple time to live for the state, which is important on the web application. So each time, on each element, basically, we delete the previous timer and we register a new one. And we clear the state when the timer is triggered. On each event processed, we extract the data from the raw event, and we combine it with the previous state if it exists. And finally, we update the states of the feature, and we merge the result with the raw event. Okay, such a design enabled us to decouple the framework runtime logic from the business rules and easily define domain-specific features for analytics and machine learning. When we deploy a new pipeline for a client, we just provide some configuration, defining the job graph, sources, things, and keys in the data to which the state is assigned, and those feature definitions. Features can depend on each other, which it enables us to drastically reduce the state size. Some features just accumulate the state, and other can depend on it and use this shared state to build different outputs. And features can be stateless and stateful. In terms of stateless features, we support multiple formats such as JavaScript, Python, JSON path, portable format for analytics, TensorFlow, and CatBoost, and others. And for stateful functions, we have tens of predefined transformations, ranging from very trivial ones such as counts or sum, to more complex ones such as approximate aggregators, sliding windows, some time-based features, and so on. And when we decouple the runtime from the business logic, we also may need to make sure that we are able to test our feature before deploying them. And that's why we provide a feature unit testing framework that's easy to use. In the simplest case, the data scientists would just have to provide the function to be tested, sample inputs, and the expected output. The testing framework evaluates all the expressions in the same manner as would be done on Flink. And we are also inspired by the Flink test harnesses, which we use to test our Flink operators and job graphs. And we implemented something similar, like our feature test harnesses that enable to test individual features with their dependencies without running the whole pipeline. Again, you can provide here some sample input, expected output, and your feature implementation. Since the jobs are running continuously and the process unbounded data streams, we had to make sure that we can easily update the logic. Fortunately, on Flink, it's really easy, either by broadcasting a control stream over your operator or by redeploying the new version of your jar. Right? What's a bit more tricky is evolving the feature state. The bigger the time interval required to populate the state, the more difficult it is. So the first thing that we try to do is to reuse the information that we already have in the state using the feature dependencies. If the exact information required is not there, we try to bootstrap it using some approximations. For example, if you want to know how much time a user spent on the site during the last 30 days, and we already have the number of page views per users, we can try to estimate the initial state of the feature. And finally, we can always load the historical data from the cold storage, maybe just one last month is enough, and reprocess it again from previously made save point. Okay, so even when we have the updated state, we need to plug it in onto the real-time processing pipeline. We can do it in a brutal way by stepping the word. By this, I mean just cancel the old job and start the new one. But this involves downtime, which in our case is problematic because for larger states, it can even take tens of minutes to make a full save point and restore the new job so that it's fully operational. So what we usually do instead is we just tell the old application A to stop processing the output using a filter pushed to the control stream at the specific to stop producing the output at the specific moment in time. And we do the opposite operation for the new job that is running in parallel. So we basically tell it, just please start writing output at this moment in time. So when the moment happens, there is no downtime. The events are processed with the new version of your application. And you can cancel the old application after all late events are processed. Okay, now I've prepared some simple demo that I'd like to show you. I hope it will work. If not, I will show you the pre-recorded video. So on the right side of my screen, you can see a simple dashboard. What's important here that all of those elements here can be modified in any way. So both those visualizations and all of the metrics that are defined here can use any attribute in the data that is available. So both in terms of metrics and how to split the data, we can also define any value from the data that we want to use. Okay, so I've prepared a sample dashboard and few features that I can show you. First, I've prepared a user group. So I want to make a simple unit. Oh, maybe this would be important. We can also view the live data stream in real time. So we can show the last 3 minutes. So it's a small data stream. We have around 7,000 events for the last 3 minutes. And I want to split my stream into two groups, A and B. For that, I need to define my feature definition. It basically needs two things. One is metadata, so how to extract values. So it informs the feature definition how to extract values from raw events. Here, I would actually need only the user ID. So just provide them values that will be extracted, and a function. Here, I prepared a simple Python function. It's just computes a hash function from the user ID and returns A or B regarding of the result. The second screen, what is it? Sorry. And now I will try to push this control feature to our dev environment. It's called user group. And what will happen right now is this feature will be, sorry, I made a mistake. So what will happen is the feature will be run, the feature will be loaded, checked whether it's correct, and serialized, and Kafka producer will be started, and the feature will be pushed to the control stream. I guess that I probably have some connection issues. Because I cannot connect to okay. I'm gonna try to debug further. I'll show it on the pre-recorded video then. Sorry for that. Yeah. So this is our mapping that was defined and our function. So this is a Python feature that will return the user group. Feature will be pushed to the development environment. And it should work on the video. Yeah, it's done. So, and what you see on the right side of what you see on the right side of the screen, the feature will be immediately available. So basically, it's the Flink process will load the feature and produce the output of immediately. So before this attribute in the events did not exist. That's why we had zeros. But as soon as it was pushed, it started producing results. So we divided our group in user groups in two groups of the same size, and it started producing output. Now, what I did is I changed the feature definition so that the group B will be smaller, like just like few percent. And after pushing the information, we have the result immediately shown here. So basically, group A will now be a lot bigger. And the last thing that I wanted to show is a machine learning function that we can push to the control stream. Here I have a simple machine learning model. It's pushed in the same manner, and when it will be pushed to the data stream, the predictions will be immediately available on the stream. So they are both in the same manner are available in the scoring API and on Cassandra for specific user scoring, and in the analytics API and the analytics platform that you can see. So we see the output predictions. We can also combine with all the other features. So for example, we have some user segments. We can see how it differs for device type, or we can also see the predictions for individual users on the bottom of the screen. Okay, thank you.